we must first examine how vision works. In order for one to see, a light source is required. Without light, everything is black. The light emits particles called photons, which bounce off solid objects in all directions before eventually reaching the eye. In order to see well, the tissue that they go through must be transparent. First, the cornea, located at the front of the eye. Then, the crystalline lens behind the pupil. Then, the vitreous body in the middle of the eye. Finally, they reach the retina, the eye's photographic plate, stopping at the retinal pigment epithelium, where they set off nerve pulses. These pulses are directed towards the optic nerve, and then the optic pathways, before arriving at the occipital brain, where the image is formed. This process is what enables us to take in the world around us.
So, as you just saw in the video, we are learning about the sense of sight today. Today's presentation will be brought to you by the Corona crew, which is me, my mom Juju, and Biscuit, our dog.
So like we saw in the video, it all starts with light. In the universe, there's light. There's pulses of energy, and that energy is transduced. And what transduce means, that's just a fancy way of saying transform. So those pulses of energy are transformed in the brain through neural messages, and then the brain processes that, and that's sight. So just to go back to what the video said, and what I just said a second ago, is it all starts with light. There's light in the universe, but what human beings can see is only a small fraction of the light that's available. And on this slide, we see through the prism. This is the part that's visible to human beings. It's different for all living organisms as far as we know, but for human beings, we can see from the violet end of the spectrum to the dark red end of the spectrum. Then we'll talk on the next slide just a little bit more about these parts of the spectrum. We live in a bright and colorful world, and as we saw on the previous slide, we see colors through a very small prism. That's how human beings experience colors. But how actually does that work? If we go back to what we saw in the previous slide with the prism, on the left we saw the blue and the violet, and on the right we saw the bright red. The way we see color is the wavelengths are quite short on the left side, and that's what gives us the blue or the violet color, and it progresses through the spectrum to the red, and those are very long wavelengths. So on the spectrum, if the wavelengths are short, we're closer to the blue. If they're long, we're closer to the red. Interestingly, the wavelengths have high highs and low lows for bright colors, and that's what's called intensity, but they have smaller amplitudes, a smaller high and a smaller low, and that's what gives us more muted colors. So the wavelengths give us the hue or the color, and depending on if they're short or if they're long, and the wavelengths, how high or how low they go, show us how bright or how muted the colors are. And one more interesting point, scientists have done labs to try to figure out how many colors we as human beings experience, and they believe that on this spectrum of color, we experience up to 10 million colors.
Okay, and now we'll talk about the structure of the eye. So, as we've been talking about, the eye needs light to see. And in this diagram, it's shown here by the candle. And the light from the candle gets sent through the cornea, which is this outer layer, and then into the pupil. And the pupil is surrounded by this muscle called the iris, which dilates and constricts, allowing different amounts of light in, and then it gets passed through the lens and projected onto the retina. And we'll talk more about the retina and the rest of it later, but scientists have found that the light actually gets projected upside down, like this candle shows. And interestingly enough, it's not actually the eye or the retina that fixes this, it's the brain later on. So, as mentioned on the last slide, we're taking a closer look at the retina. And here, it's the cellular level of the retina. And once again, it all starts with light. The light comes in and activates these rods and cones buried deep inside the retina. And there's millions and millions and millions of these rods and cones, which then cause a chemical change and activate these bipolar cells. The bipolar cells then activate the ganglion cells, and the axons of the ganglion cells form this rope-like superhighway for messages called the optic nerve. And the optic nerve then sends these messages to the brain's visual cortex through the thalamus. And an interesting fact is this part right here, this little hole in the optic nerve is actually a blind spot in our eye. And we'll talk about that more on the next slide with an activity, but you actually cannot see anything right there because there's no rods or cones anywhere, so nothing gets activated. And yeah, we'll talk about it more on the next slide. So, as I mentioned on the last slide, we're going to be talking more about our eye's blind spot. And it's kind of like the blind spot of your car. When you're driving, you got to keep checking over your left shoulder so then you don't run into any cars while you're switching lanes or anything and ultimately die. So, our eye actually has a blind spot just like this. And for this, we actually have an activity coming up. Woo! For this activity, all you need is one piece of paper, a note card, and a marker. You're going to want to draw an X on the right side of the note card and then a dot on the left. And then you're going to want to cover your right eye with your hand and then make sure the X is on the right and hold it out at arm's length. Concentrate your left eye on the X and then slowly move it closer until you cannot see the dot. Like right now, I cannot see the dot.
Are you blind?
No, I'm not blind. It's just our eye's blind spot. Don't believe me? Try it out yourself. So, now that you've done the blind spot activity and have experienced it firsthand, let me repeat why this happens. So, as I explained on the last slide, the retinal has a little hole that's created by the optic nerves. Those are the things that send the messages to the brain's visual cortex, and it creates a little hole or tunnel. And in that hole or tunnel, there's no light receptors or rods or cones, so nothing gets activated and no messages get sent. So it's like your eye doesn't even see it, and which is why it's called the blind spot. I've been talking a lot about the cones and rods over the past few slides, and here's just a bit more information about that. So we have this beautiful graph over here, and it talks about cones and rods, of course, and there's 6 million cones and 120 million rods. And we'll talk about the cones first. They're located in the center of the retina, and that's also called the fovea, and they have a direct pathway to the brain, so they're a bit more rare than rods, as you can tell by the number. And what these kind of mean down here is the sensitivity in dim light is low, because if you think about it, when there's not a lot of light outside, it's dark, right? And you can't really tell what color a tree's leaves are. You can tell there's a tree and there's leaves, but you can't tell if they're green or like orange, right? So they need a certain amount of light to be able to show color. And the rods, on the other hand, they're like the more black and white colors. So they're much more basic, and and they're located on the periphery of the retina, and that's like, and don't have a direct pathway to the brain. And basically, cones show color, rods are more black and white, and cones are more detail oriented, and they have different tasks throughout the retina. And up here you can see, I don't know if you can see, but there's like a little picture of rods and cones, and that's what they look like. So now I have another demonstration or activity for you, and pretty much all that you're gonna have to do for this is stare at the middle of the screen. So there's gonna be a flag. It won't be the American flag like this, it'll be the Italian flag. You're just gonna want to stare at the middle. There should be a black stripe because the colors will be inverted, but there's gonna be a stripe in the middle. Just stare at the middle until the screen turns all white, and you'll see this image, and it'll be really cool. Just check it out. So after watching that, hopefully you experienced the same thing that I did, and you could see the Italian flag even after the inverted colors disappeared, and it was just a white background. And you might be wondering, why does this happen? And the reason it happens is because there's 3 different types of color receptors or cones, and those are red, green, and blue. And once these cones get tired and there's a white background, they're kind of lazy and they just kind of keep showing the color or the inverted color. So that's why once there's a white background plus the tired reactors, it creates an after image, which is what you just saw, and it's pretty interesting.
Okay, so I think this slide kind of sums things up. What we said at the beginning of the presentation is it all starts with light. So the retina takes the light and it sends the information to the brain in the following way. The retina sends it down the optic nerve. You can kind of see those highways of the optic nerve. And then that sends the information to the thalamus. And the thalamus then relays the information to the visual cortex in the occipital lobe. I'll talk just a little bit more about the visual cortex in the next slide, but I wanted to point one thing out, which I thought was very interesting, and the book makes mention of this, is that the retina itself is not a part of the eye, but the retina is actually brain tissue, and the brain tissue forms in the retina while you're still a fetus. So the eye, the back of the eye, the retina, is actually part of the brain. I thought that was pretty interesting. So when we started this presentation, we started with light. That's how we started most every slide. And what is also interesting is that at the beginning of the book, the section on sight, is it talks about a young woman who couldn't recognize people's faces. So how did we get from light to faces? Well, that's what that's the aim of this slide, is to talk a little bit about feature detection. So there's feature detector cells that are located in the visual cortex. And what those feature detector cells do is they pass information to these supercell clusters, and the supercell clusters respond to complex patterns. And those patterns form categories. Like, for example, there's a category of faces, or a category of houses or chairs. And interestingly enough, these are located in different parts of the brain. So as the example in the book showed, the young lady must have had some kind of a damage to the part of her brain, which I think is shown in red here, the faces, and she couldn't recognize people's faces, but it was very easy for her to recognize a house. So I thought that was very interesting, and that concludes the slides. And
Biscuit.
there's our biscuit.
Okay, and now to wrap it up, I hope that you can see now that there's more to the sense of sight than meets the eye. Thank you to our sponsors of this video, our dog Biscuit, and YouTube really helped us out on this one. And I hope we'll see you again soon.